Today we are going to talk about the Beckmann's rearrangement. So this is one of the important rearrangement in the examination point of view. So in the Beckmann's rearrangement, if you will see, oximes will get converted into amides. So here we have two things we have to remember. One is aldoximes, another one is ketoximes. So oximes means it can be either aldoxime or ketoxime, but aldoximes are not reactive in the Beckmann's rearrangement, only ketoximes are reactive. Why, we will see now. So when we have an aldehyde which is upon treatment with the NH2OH, there is an elimination of water molecule and which leads to form RHNOH. So this is called aldoxime. So this aldoxime will exist in two forms that we'll see later. And now we have a ketone, and this is upon treatment with NH2OH. There is a elimination of water molecule and it leads to form RNOH. So this is called ketoxime. So now we'll go for the aldoxime. So aldoximes will exist in two forms. This is a one form, and another form will be and lone pair is here, OH is here, R and H. So if we will give the E and Z nomenclature, so this will be 1, this will be 2, and this side this will be 1 and this will be 2. So both are in opposite direction, so this is called E aldoxime, and whereas this is called Z aldoxime. So in this case, in case of E aldoxime, there is a syn elimination will takes place, minus H2O in the syn elimination takes place, and it leads to form a nitriles. And similarly in the Z aldoximes also, there is a anti-elimination takes place. In case of Z aldoxime, anti-elimination takes place, and here also we will get a same product, that is a nitrile product. So this is not a Beckmann's rearrangement. Here just we are removing the water molecule, so we are ending up with the nitriles. So whereas if we will see the ketoximes, here that possibility is not there, because here we have a alkyl group. So there is no point that there is a elimination of water molecule in this case of in the ketoximes. Only in aldoximes there is a possibility for the elimination of water molecule, so that we will get nitriles from the oximes, whereas in case of ketoximes there is no possibility to the elimination of water. So in case of ketoximes only we will see the Beckmann's rearrangement, whereas in case of aldoximes we will not see the Beckmann's rearrangement. And then we will see the mechanism, how it goes. So here we have N OH, and here lone pair is there, and here we have a benzene group and methyl group. So now we will see the Beckmann's rearrangement for this compound. So now we have a first step is the protonation, because in the Beckmann's rearrangement we are using a acid. So that acid will give the H plus. So that H plus will be attached to this OH. So now it will get converted to OH2 plus CH3 like this. Next, now just remember that In the Beckmann's rearrangement, there is a migration of one group will get migrate. That group, the one group which is going to migrate, that will be the group which is present exactly opposite to the OH. So here we have two groups, methyl group and phenyl group. So phenyl group is present exactly opposite to the OH. That means OH, this phenyl group will migrate, not methyl group. So whichever group is present opposite to the OH, so that group will get migrate. Okay. And during migration, in the transition step, this is the rate determining step because this is slow step. And here we will see this kind of transition step. So here we can 6-member, and this one only will form a bond to nitrogen also. So here we can say 3-member transition state. So 1, 2, 3, 3-member transition state. We know that 3-member transition state is not that stable. So now this water molecule will get eliminated, and here we have pH, and now here we have a positive charge, and here we have a methyl group. And further, because this positive charge is coming because of this phenyl group is migrating from this carbon to this nitrogen, and now we have a water molecule. So this water molecule, the water molecule which is leaving from the reaction, that will not be coming again. So this is the fresh water molecule which we already have in the reaction mixture. So that this water molecule comes and attacks to this carbocation, and it leads to form OH and double bond here N pH, and here so now this is enol form. So we know that enol form is not that stable, so it undergoes tautomerization and it leads to form keto form. So this is amide. So we started with oxime, and we started with oxime here, and we ended with the amide. And further, if we will hydrolyze this one, so we'll get a carboxylic acid and amide. Okay, so this is the Beckmann's rearrangement. So in the first step, H plus comes and attacks to the OH. So then in the next step, there is an elimination of water molecule and followed by the migration of the group which is present opposite to the OH. Okay, so here phenyl group is present opposite to the OH, that means phenyl group is migrating. So during migration step, there is a 3-member transition state will form, and further we have a carbocation formation here, and further water molecule comes and attacks here, it forms enol form, and further we will get a enol form will get converted into keto form, we will get a amides here. Okay, and next there are we have two kinds of Beckmann's rearrangement. First one is intramolecular Beckmann's rearrangement, and the second one is intermolecular Beckmann's rearrangement. So what is the difference between these two? In case of intermolecular Beckmann rearrangement, the stereochemistry will retain. No change in the stereochemistry, whereas in case of intermolecular rearrangement, stereochemistry is invert, will get invert. So now we will see with the examples. So here we have N, a lone pair here, OH, and here we have a pH, CH3 and hydrogen. I think this question asked in GATE exam in 2014, I think 14 or 13, and here methyl group is there. So now we have a proton source here, H plus attacks to this OH, and it will become OH2 plus a lone pair here and CH3. Here we have pH, CH3, hydrogen. So as I said earlier, the group which is present exactly opposite to the OH, that group will get migrate. Here this group is present here, means this group is present opposite to the OH, so that means this group is migrating. So you will remove this and this group will migrate from here to here, so that we'll get CH3 here, positive charge, N, so pH, hydrogen and methyl and hydrogen, then here positive charge we have. And next we have a water molecule, and that water molecule attacks here, it forms enol form. I mean I directly wrote enol form, it actually attacks like this, but I wrote enol form only. And then pH, here we have methyl and hydrogen. So now we have enol form, so there will be tautomerization. Because of that tautomerization, enol form will get converted to keto form. So that keto form looks like this: N, pH, methyl and hydrogen, and here NH. So here, as we can see in the reaction, starting precursor, pH is present above the plane, and in the product side also pH is present above the plane, and whereas methyl group is present below the plane, and here also methyl group is present below the plane, means stereochemistry is retained. So stereochemistry retained means that comes under the intramolecular Beckmann's rearrangement. Okay, now we'll go for the intermolecular Beckmann's rearrangement. Here we have intermolecular Beckmann's rearrangement. Here we have CH3 and double bond N, OH, lone pair here, and H. So this is the starting precursor here. So as we can see, in case of intramolecular Beckmann rearrangement, in case of intramolecular Beckmann rearrangement, the group which is present opposite to the OH is some functional group. Here is a phenyl group. Whereas in case of this case, here the exactly opposite group is this group. Okay, so here this is not possible that this group will migrate. This group will not migrate. So here the mechanism is different. So here we'll see the mechanism how it goes. In the first step we have a H plus, and that will attacks to this OH, and it leads to form CH3 here, double bond N, OH2 plus, and they will fire here, and hydrogen here, and there is an elimination of water molecule. So upon elimination of water molecule, what will happen? This water molecule will eliminate, and this carbon bond will migrate like this, and it will becomes hydrogen here, and this will become CH3 triple bond N, and there is a positive charge here. Now as we know that nitrogen is more electronegative than carbon, the polarization will take place like this, and there is a negative charge on the nitrogen, and so here negative charge will come, that negative charge comes and attacks here. And here we need to remember that the whatever position is there in the starting precursor, here simply we can say it follows SN2 mechanism. Means not exactly, means I am trying to say that here it is present, here is present in the above the plane, but this nitrogen comes attacks from the below the plane. Okay, then it will become like this. This should be a below the plane, and double bond CH3, and here positive charge and hydrogen. Now we have a water molecule, that water molecule comes and attacks here, then it will become double bond OH CH3 and hydrogen, and further for tautomerization we will get a keto form. So here in case of intramolecular Beckmann rearrangement, the stereochemistry will retain, whereas in case of intermolecular Beckmann rearrangement, stereochemistry is inverted. Here it is a stereochemistry cis, whereas in the final product stereochemistry is trans. So this is about the Beckmann's rearrangement. Now we will going to see Beckmann's rearrangement in a cyclic compounds. So now we'll take a cyclic compound, cyclic oxides. We have double bond N OH. So in the first step, protonation will take place. So in the next step, see here the group which is present exactly opposite to the OH is this carbon, and this carbon opening takes place, means while removing this one, this opening will takes place. So then it will become, so here negative charge, here positive charge is there, just imagine like this. Okay, so now for our convenient we will give the numbering 1 2 3 4 5 6, and these two will form a bond here. So then it will become a 6-member ring. So in the first place nitrogen will come, so there is a double bond between 1 and 2, so that double bond comes here, and 3 4 5 6. And also here we need to remember that here this bond is polarization will take place like this, and here we will get a positive charge, because here we are getting negative charge, means this carbon will get a positive charge. So that positive charge is there on the second carbon, right? So that positive charge comes here. And now water molecule come into the picture. Then it will become OH. So as we know that this is enol form, then we'll get a keto form here. Just remember, in case of cyclic oximes, when it involves in Beckmann rearrangement, ring expansion takes place. So here is a 5-member ring, and it became a 6-member ring. Okay, and we'll see other examples also. So here we have a 6-member ring, double bond NOH, so now it's very simple. so we don't need to go for mechanism, okay, because we have already done it. So here 6-member ring is there. So as we know that in case of cyclic oximes, ring expansion takes place. So that ring expansion means like a 6-member ring will get converted to a 7-member ring, and which forms amides. Okay, next here we have this kind of compound double bond NOH. Okay, so here H plus goes and attacks to this OH, and it will become like this double bond NOH2 plus. And now this bond, this polarization goes like this, and there is a negative charge here, and there is a positive charge here, and one more positive charge is here. And now these two will form a bond. We can give numbering here: 1 2 3 4 5 6. A 7-member ring is forming here. So this finally looks like this. Here I am writing directly product NH double bond. Okay, so this is the product here we'll get. And similarly, when we have a this kind of compound, we have 2 oximes here, and when both oximes will involve in the reaction, the final product what we will get here is NH CO CO NH. So this is the product here we will get. So here both the oximes are involved in the reaction. Nothing here, just you need to remember that this is OH, opposite to that this is present. So this will open like this, and this will open like this. So because of that, it will become a, we'll get this compound. Okay, so next we have this kind of compounds. Whatever examples now I am going to discuss, they are very important. So like we have spiro compounds. So this is called spirocarbon and OH. So mechanism is simple here, so no need to worry about this. And we have H plus here, then it will become double bond NOH2 plus. So here the group which is present exactly opposite to this OH is this carbon, right? So this carbon, we do numbering 1 2 3 4 5 6. So this carbon, and going to imagine that if it comes like this, okay, then it will become N plus, and again here plus, and here negative charge is there. Now these two form a bond. Here we can give 1 2 3 4 5 6 member ring is forming. If you do numbering, it's very easy to predict the product. If you don't, then it will be difficult. So this will be 1 2 3 4 5 6. At the second position we have positive charge, and at 6th carbon we have a spiro compound. And further, after treating with water molecule, we will get this compound. Okay, so this is the compound here we will get. And another example here we have, that is let's imagine that we have a 6-member ring here, and this kind of compound. And here also, wherever Beckmann rearrangement is going, that their ring expansion will takes place. So here is a 5-member ring and it became a 6-member ring, and here it is a 6-member ring and it will become a 7-member ring. So this is the compound here we will get. And then here we have another example. Methyl is here. This. So this comes under, we can say this comes under intramolecular Beckmann rearrangement, and here we will get product NH CO CH3. So this is the product here we will get. And there are some effects in case of Beckmann's rearrangement. First one is solvent effect. It's very, very important. Second one is migratory group effect. And third one is living group effect. And fourth one is like what else are there? Acid catalyst. So these are very simple effects which we can remember very easily. Just we'll follow the mechanism. So from there it's very easy to remember. So first we will go for the solvent. Solvent means there are two solvents. We have a polar solvents and non-polar solvents. Okay, so the fundamental thing is if any charged species is involved in the reaction, so then we'll go for the polar solvent. If non-charged species is there, then we'll go for the non-polar solvent. And if we see the mechanism of Beckmann's rearrangement, so here we can see in this step there is a positive charge is there. So since there is a charged species is involved in the Beckmann's rearrangement, so polar solvents are favorable for Beckmann rearrangement over the non-polar solvents. So the reaction when we will use the polar solvent, their reaction goes very fast. When we will use non-polar solvent, the reaction goes very slow. Next, migratory group. So as we know that electron-rich groups will involve faster in the migration. So here we have two examples. So here we have toluene group, and here we have methyl group, and similarly we have OH. Here we have a phenyl group and CH3. So here opposite to the OH, toluene group is present. Opposite to OH, here phenyl group is present. And now we need to see which one is more electron rich. Obviously the benzene with methyl group is electron rich compared to phenyl group. So because of that reason, this reaction goes very faster compared to this. So this is about the migratory group. This is faster compared to this one. And the living group, so better living group is there, means that goes reaction very fast compared to non-better living group. And acid catalyst. So as we seen in case of mechanism of Beckmann's rearrangement, the first step is the protonation. So from where this H plus is coming, this is coming from acid catalyst. Let's imagine that we have formic acid and acetic acid. So which one gives H plus very fast? Obviously formic acid gives H plus faster compared to acetic acid. So because of that reason, if we have a strong acid, there Beckmann's rearrangement is very fast. When we have weak acid, there Beckmann's rearrangement is slower. And these are the effects involved in the Beckmann's rearrangement. And then there are some previous questions on the Beckmann's rearrangement. So those questions we are going to talk now. Methyl pH, methyl and hydrogen. In the first step, tosyl chloride and pyridine is there. In the second step, water molecule is there. This question asked in GATE 2013. Okay, so this is also just Beckmann's rearrangement. Instead of acid catalyst, they have given a tosyl chloride. So this tosyl chloride will get this OH will get converted into OTS here. In OTS pH, methyl group, hydrogen, methyl. So this leaves like this, and this whole group will migrate from here to here, and here we'll get N double bond, sorry, pH, methyl and hydrogen, and here positive charge, methyl, and water molecule is there. Finally we'll get this compound. So this question asked for 2 marks in GATE 2013. So Beckmann's rearrangement is one of the scoring rearrangement because it's very simple. And another question we have here, that is we have NH2OH. In the presence of HCl, this first step, and second step we have tosyl chloride in the presence of pyridine, and third step we have heating, and fourth step we have water. So this step we know that here oxime will form, and next step we know that oxime will get converted into OTS, right? So I'm writing final step, means from here I am writing OTS will come. Okay, so now this whole group will migrate from here to here. Then it looks like and in the final step we have a H3O plus that will becomes, I'm not writing any groups here, I'm directly writing here only methyl group forms here, N double bond CH3 OH H. There is a positive charge. Okay, and now this positive charge goes and attacks here, and this, the final product will be CH3 here, oxygen, and double bond in this one. So this is the final product we will get. So this is also very simple, but only the structure is very big. So in the first step, we know that here we have ketone and NH2OH, so here we will get NOH. This is the first step. In the second step, we have tosyl chloride, you will get a OTS. And the next step, this whole group will migrate from here to here, then it looks like this, a positive charge. And further water treatment, we will get this, and there is a intramolecular reaction takes place, and there is leads to form a 5-member ring here. So this question also asked in the GATE exam. And the next question asked in the GATE exam only, that is this one. This is favorite reaction for GATE exam. So here we have NH2OH, it's 90%. This is Y upon treatment with H2SO4, 70% Z. So we need to identify. So this A is very simple, that is double bond NOH. And next we have a Beckmann's rearrangement. Here we know that the ring expansion will takes place. In case of cyclic oxime, ring expansion will takes place. So this ring remains a 6-member ring here, and there is a 7-member ring formation. So this is the answer. So this is about the Beckmann's rearrangement. This is one of the famous topic for GATE chemistry. So I hope all things got cleared here about the Beckmann's rearrangement. The main thing here we need to remember is the group which is present opposite to the OH, that group will get migrate. So that we need to remember. Okay. And next one, we have to see intramolecular Beckmann's rearrangement as well as intermolecular Beckmann's rearrangement. In case of intra, the stereochemistry will get retimed. In case of inter, stereochemistry get inverted. And cyclic oximes also very important. In case of cyclic oximes, ring expansion will takes place. So this is about the Beckmann's rearrangement. Thank you.